Good morning, class. Here's elementary statistics, practice test number 5. Module 5 covering chapters 10, 11, and 12. Here's chapter 11, goodness of fit and contingency tables. Again, reminding everyone about the pledge. When we take the exam, I pledge on my honor that I will neither give nor receive unauthorized systems, so on and so forth. You may use formula sheet, tables, and a graphing calculator. All right, chapter 11, goodness of fit and contingency table. Number 1, goodness of fit test in multinomial experiments. Here are the observed frequencies from 4 categories, 5, 6, 8, and 13 at 0.05 significance level. That means alpha. Test the claim that the 4 categories are all equally likely. Here's the test of hypothesis, different steps. State the null and alternative hypothesis. What is the expected frequency for each of the 4 categories? What is the value of the test statistics? Find the critical values, make a decision. So let's look at a couple of definitions, starting with definition. A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claim distribution. Goodness of fit hypothesis tests are always right-tail tests. If the sum of this weighted square deviation, chi-squared is summation of O minus E quantity squared over E. O stands for the observed value, E stands for the expected value, is small. The observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from the distribution, from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, the chi-square goodness of fit test is always a right-tail test. So having said that, the formula that we use, E is N over K, E equal frequency, or E equals N times P, the proportion. So we are going to use E equals N over K. What is N? Summation of O, observed value. So as we look at this question, here are the observed frequencies, 5. So summation of those 5 plus 6 plus 8 plus 13 would be summation of O, or the observed values. And you're going to divide by how many? 4. And it becomes 8. So given it's a multinomial experiment because K equals 4 categories, 1, 2, 3, 4. Alpha is 0.05, use a goodness of fit test. Each expected frequency is 8, thus satisfy the requirement of being a value at least 5. It's important for this to be larger than 5. Why is that? Expected count less than 5 makes the chi-square test unreliable because it violates the approximation assumption that ensure the accuracy of the p-value and test statistic. It has got to do with the essence of the test. That's why statistical guidelines require all expected frequency to be at least 5. 8 is good. We are in good shape, so we can move on. All right, now we're going to continue on that thoughts. Again, I want to remind you that here's the test statistic, chi-squared, the summation of O minus E quantity squared over E. Degrees of freedom is K minus 1. K is the number of categories, and E is N over K, or summation of O over K. And we found this to be 8 from our early calculation. So here's the test of hypothesis, H0, P1 equals P2 equals P3 equals P4. In this case, we are saying the probability or proportion for each category is the same. That's the meaning of it. And that is the claim. And H1 would be that at least one of them is different. So at least one of the probabilities or proportions is different from the others. Okay, so there are four of them. That means there should be 1/4 or 0.25. That's the concept. So we got the first step. The second step is the test statistic using this formula. Again, you may do this with technology, but I want to show you, it's a small, sample, how we do this by hand. So test statistic chi-squared is summation of observed value minus expected value quantity squared over E. In other words, we start with this one, 5 minus 8 quantity squared divided by E, which is 8, plus 6 minus 8 quantity squared plus 8 minus 8 quantity squared plus 13 minus 8 quantity squared. And we can divide them in one shot divided by 8 instead of doing them, individually. So that's 5 minus 8, 3 squared, 6 minus 8, negative 2 quantity squared. So this is 9, this is 4, this is 0, this is 5 squared, 25. They add up to 38 over 8 or 4.750. The next step is to find the critical value. From the choice of alpha, which is 0.05, degrees of freedom 4 minus 1 or 3, from the chi-squared table. So on the left column, we find the degrees of freedom 3. At top, we find the area 0.05, the area to the right, and we take this to be a right tail test. They put together 7.815. Chi-squared is 7.815. So let's do the drawing so it becomes clear. It is skewed to the right. Here's the critical value. Where does this land? Way into the non-rejection region. The decision, therefore, would be do not reject H0 or fail to reject H0. That's a better terminology. So let's go back to step one. Here's the claim. If you are not rejecting H0, that means the claim becomes true because it's part of H0. That's why you make a decision in the beginning. So the claim becomes true. So what is the claim now? You are going to reinstate. There is sufficient evidence to support the claim that the four categories are all equally likely. That's it. Now, just in case, if we assume this is a two-tailed test, that means for one case, the area to the right, where is that? Alpha is 0.05, half of that, so 0.025. Okay, so in other words, if you have two values, the one to the right of it is 0.2025. Let me just quickly show you. That means this area is 0.025. This area is 0.025. So this case, the area for the chi-squared of the left area to the right is 0.975. So if those were the values, clearly look at the test statistic. It's also in between those two values. You get the same result, okay? So chi-squared of the left, alpha is 0.975, degrees of freedom is 3.216, and the other one is 9.348. But in any event, let me erase my work. This is in case. As far as technology is concerned, how does that work? You use the TI calculator, goodness of fit test, stat edit, and you're going to clear list L1 and L2. The observed value, you put it in L1. The expected value, you put it in L2. The observed values are 5, 6, 8, 13. The expected value is 8. In L2 goes all number 8. Okay. So then you do goodness of fit test, stat test, chi-squared GOF, goodness of fit. Enter L1 and L2. Degrees of freedom is N minus 1. So when you do that, this is the L1, this is the L2. Notice L2 is all 8s. And so observed is in L1, expected is in L2. You're running the chi-squared. Degrees of freedom is n minus 1 or 3. Now you do the calculation. What do we get? First and foremost, notice the test statistic is calculated for us. Now, as far as technology is concerned, they go with the p-value. Of course, degrees of freedom is 3. And what is this one? This is the p-value, 0.191, way larger than alpha of 0.05, and you get the same decision. Fail to reject H0. Very straightforward, everybody. I hope everybody is fine with that. Okay, we're going to continue with that goodness of it test. A professor asked 40 of his students to identify the tire they would select as a flat tire of a car carrying 4 students who missed a test. An excuse, of course. The following table, this one, summarizes the result. Use a 0.05 significance level, alpha, to test the claim that all 4 tires have equal proportions of being claimed as flat. There are 4 tires. That means, of course, proportion is 1/4 or 0.25. So, by the way, what is this one? Capital L is left and capital R is rear, lowercase r is right, and so forth. So, for example, LF, left front, 11 said so. Right front, lowercase rf, 15 said right front. Left rear, 8. Right rear, 6. So just starting with that. So E is N over K. There are 4D students, divided by 4, or N, in this case again, 4D students times P. The proportion for times would be 1/4 or 0.25. Either way, we should get 10. And so let's get started. Each expected frequency is 10, does satisfy the requirement of being a value of at least 5. So we have no problem. That's important to understand. So having said that, step 1, H0, probability of left front and right front and so on, they're all the same. And they happen to be equal to 0.25, and that is the claim. H1, at least one of them is different. At least one of the proportions or probabilities is not equal to 0.25. P sub I is not equal to 0.25, which makes it a two-tailed test in general. But remember the restriction of chi-squared, we make this a right-tailed test, but I'll show you both values and listen. We calculate the test statistics, so that's the second step. Summation of observed minus E quantity square. Again, we have just a few, so it's really not too bad. We're going to start with this one, 11 minus 10 quantity squared, okay, plus 15 minus 10 quantity squared, plus 8 minus 10 quantity squared, plus 6 minus 10 quantity squared. All of them we divide by the expected value, which is 10. You do the math, 46 over 10, 4.6. Critical value happen to be the same as what we had in the previous page. CV alpha is 0.05, degrees of freedom is K minus 1 is 3, and chi-squared is 7.815. We already had that. And if you do the drawing, clearly the test is, so this is the critical value. The test statistic is here, 4.6. And we see that fail to okay, don't reject H0 or fail to reject H0 because it's the test statistic is way into the non-rejection region. And don't reject H0. When you don't reject H0, the claim becomes true. There is sufficient evidence to support the claim that all 4 tires have equal proportions of being claimed as flat. That's the meaning of it. And again, if we were to go with the two-tailed test, the same numbers for the other one. So this test statistic is in between. You see that? So we get the same result. And it's important to understand the meaning of it. When four students identify the flat tire, it is not likely for all to select the same tire because each tire has the same probability of 0.25. And as far as technology, by the way, is concerned, I want you to know that the p-value would be the area to the right of test statistic to the right of 4.6. So this is the p-value that can be figured out either from the table or technology. Either way is fine. All right, let's elaborate on this stuff. So reminding you what's a contingency table. A contingency table or two-way frequency table is a table consisting of frequency counts of categorical data corresponding to two different variables. One variable is used to categorize rows, and a second variable is used to categorize columns. When data can be tabulated in table form in terms of frequency, several types of hypotheses can be tested using the chi-square test, such as the test of independence of variables and the test of homogeneity of proportions. And while they use similar methods, they serve different purposes. The test of independence evaluates whether two categorical variables in a single sample are statistically independent. It tests the null hypothesis that there is no association between the row and column variable in a contingency table. That is, there is no dependency between the row variable and column variable. In the test of independence, observational units are collected at random from a population, and two categorical variables are observed for each unit. Purpose: to determine if two variables are related within one population. Data structure: one sample, two categorical variables. Example: gender and voting preferences. Question: it answers: is there a relationship as associated association between variable A and variable B in one population? Is there an association between gender and preferred type of exercise? So that's the test of independence. So chi-square test of homogeneity. Test of homogeneity of proportion is a test of the claim that different populations or groups have the same proportion or distribution of a single categorical variable. The test of homogeneity of proportions is used to determine whether the proportion of a variable are equal. When several samples are selected from different populations, it tests if the proportion of categories are the same across different groups. Now, test of homogeneity, the purpose is to compare the distribution of a categorical variable across two or more populations. Question, it answers: are the proportions of a categorical variable the same across different groups? Data structure: multiple samples, one variable, example preference across age groups. Example, do three age groups differ in their preferences for a political candidate? Both tests use the chi-square test and are computed similarly using contingency table, but their design and hypotheses differ. All right, let's look at the feature: test of independence, test of homogeneity. The test of independence used for relationship between two variables. Test of homogeneity, comparing groups on one variable. Sample structure: one sample with two variables, or test of independence. Multiple samples, groups with one variable. Goal for test of independence, test for association, for homogeneity, test for equal proportions. Typical wording of null hypothesis: variables are independent. For test of independence, proportions are equal across groups. Tests of independent and tests of homogeneity are always right-tailed. If the sum of these weighted square deviations, summation O minus E quantity squared over E, is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, test of homogeneity is always a right-tail test. In fact, again, both of them, of course, right? All right, okay, this is a test of the independence. Using a 0.05 significance level, test the claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or girl. So here's the table, everybody. So the given. So these are the survivors. These are who didn't. Men, for example, this means 332 men survived, 1,360 died. Women, 318 survived, 104 died. Boys, 29 to 35. Here's 27 to 18, just to give you an idea as to what's going on. Now, let's sum them up. In this group, when we add these two numbers, we get 1692. These two numbers, 422. These two numbers, 64. These two numbers, 45. Okay. And how many survive? Add 332, 318, 29, and 27. How many died? Add these four numbers. So we have the total. So this number is the grand total. Okay, so understanding the table. So this was given. We created a total along the columns, okay, the rows, and this is the grand total, if you now. Expected frequency E equals row sum times column sum over grand total. Row sum times column sum over grand total. Use the formula to find expected frequencies for the upper left hand set. So the idea is that this is what we have observed, but what would be the expected value, okay, in the case of being independent? So the observed value is 332 for this cell. According to this formula, the value should be the row sum, which is 706, times the column sum, which is 1692, and then divided by grand total, which is 2223. Okay, so multiply these two, divide by this. So although 332 survived, the expectation would have been this number, although this is not a whole number, and it's, we're dealing with a discrete variable, so it has to be a whole number, but this is an expectation, so you can keep it as such. So using the same procedure, the table of expected values, so we do the same thing. So we did it for one cell. We do for each and every one of them, and it creates the following. So again, this was done. If you were to do it for this cell, it becomes 134.022 and so on. So interpretation. to interpret this result for the upper left hand for this one. Although O is 332 men survive, that is the observed, that is what happened. We would have expected this many, equals 537.36 men to survive if survivability is independent of whether the person is a man, woman, boy, or girl. So being, okay, to survive and being a man or a woman or a boy or a girl if they are independent. There is a discrepancy between these two values. And such discrepancies are key components of the test statistic, that is a collective measure of the overall disagreement between the observed frequencies and the frequencies expected with independence between the row and column variable. So to interpret this result for the lower left-hand cell, okay, for this one, O equals 1,360 men. Okay, so we can say that although O, the observed value is 1,360 men actually died, we would have expected this many, 1,154.64 men to die if, again, survivability is independent of whether the person is a man, woman, or boy, or girl, which is not the case. Note, summation of E in row and column are consistent. If you look at column 1, for example, whether we add 332 and 1360, we get 1692, or if we add the expected value, we must get the same number. The only reason it may be slightly different is due to round-off error, but they will be extremely close, if not identical. Same thing here. If you add these 4 numbers, you get 706. If you add these 4 numbers, you must get 706 as well. And that is important for it to work that way. All right, let's actually go to work. So we are going to, this is what we have, okay, and we're going to get started. So requirement, let's assume random selection. Results are frequency, and E is larger than 5. As you can see, the expected value for each cell is larger than 5. The smallest value is 14.291, so we are fine. H0, whether a person survived, is independent of whether the person is a man, woman, boy, or a girl. The row variable is independent of the column variable. They both mean the same thing. And that is the claim. Surviving the Titanic and being a man, woman, boy, or girl is dependent. In other words, the row variable is dependent or related to the column variable. And it's a right take test. So we're done with the first step. The second step is the test statistic using the formula chi-squared is summation of O minus E squared over E. Degrees of freedom is R minus 1, C minus 1. R is the number of rows. C is the number of columns, okay? So how many rows? 1 and 2. How many, so 2 minus 1, 1. 1, 2, 3. How many columns? 4, 4 minus 1. So 2 minus 1 times 4 minus 1. Degrees of freedom is 3, just for the sake of argument. But having said that, how do we calculate this? If we stick with the very first entry, okay, the difference between these two quantities, and it doesn't matter which one comes first, but normally O minus E. In other words, 332 minus 537.36 quantity squared, plus the next one is 318 minus 134.022 quantity squared. We do the same thing, all of it to the end, to the last one, plus 18 minus 30.709 quantity squared. And each case we divide by its own E. So the first one is divided by this number, the second one by this number. So for example, this one is 537.6, this one is 30.709. So this is the way you do the division. And you do the math, you end up with 507.084. That is the test statistic. I mean, clearly it's a huge number where as the critical value comes from the degrees of freedom and alpha. Alpha is 0.05. Degrees of freedom is R minus 1 times C minus 1. There are 2 rows, 2 minus 1, there are 4 columns. So 3, and we already have this number. Really, I mean, this is way larger than that. If you do the graphing, this is the critical value, and this chi-squared is, you can't even tell somewhere here. I'm just showing here, but it's way, way into the rejection region, and obviously the result is reject H0. And if you're rejecting H0, the claim becomes false, right? Because claim belongs to the first one. So there is not sufficient evidence to support the claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or a girl. In other words, survival and gender are dependent. Survival and gender are dependent. As far as technology is concerned, TI calculator and contingency table, we access the matrices using matrix second and press X to the power minus 1, edit, enter, and then we do the test. So matrix is a 2 by 4, and we're going to go with matrix A, and we're going to put the observed values 332, 318, 29. I don't have room to show you 27. The next one is 1360, 104. This is 35, and again, I don't have room to show you the next one, which is 80. So what happens? We're going to run the test. This is a chi-squared test. We choose the chi-squared test. The observed value is A, the expected value is B. This is what they choose, automatically. What happens is that when make sure that it mentions A, this is the one which will be created. In other words, remember the highlighted numbers, the E, the expected value, we did that by hand. It will be calculated and will be put in matrix B. So the chi-squared test gives us this and B. Notice again, if you look up the B matrix is your expected value. So the expected value will be done for you. And what do we notice here? Obviously, here's the chi-squared that we calculated. Of course, slightly different because this uses more decimals. And p-value is 0 because it's the area to the right of this number. So there is really not much there. So p-value from the chi-squared table, okay, if you go with the table, we don't have that. And this is larger than highest value. In the table, we have 12.838. So the p-value, it just writes that it's less than 0.05, which is the alpha. So, but if we go with the technology, okay, it's 0, less than alpha, and we have the same decision. Pretty straightforward. All right, test of homogeneity using the following table with a 0.05 significance level, test the effect of pollster gender on survey responses by men. So what do we have here? Men who agree, men who disagree, a gender of interviewers. So for example, if the person that is doing the interview is a man and questioning another man, we get 560 that agree, but those who disagree is 240. But it makes a difference if the interviewer is not a man, is a woman. Now the answer changes to 308 here and 92 here. So that's the concept. So having said that, again, reminding you of the test of homogeneity, we already went over that. The test of homogeneity of proportion is a test of claim that different populations or groups have the same proportions or distributions. We've already discussed. So, and they're right. So having said that, we are going to come up with the total here is 800 and 400. Here, add these two, and this is the grand total. And so the formula for expected frequency row sum, column sum over grand total. Okay, and so we have the table of expected value, which is this one. And how do we come up with that? For example, for one of them, for 560, okay, we are going to, for 560, we're going to multiply these two. Remember, row sum and column sum, these two, and divide by this. That's 578.67. Again, we've already discussed that, so it should be fairly easy. And this is how you come up with that. As far as requirements are concerned, based on the description of the study, we will treat the subjects as being randomly selected and randomly assigned to the different posters. The results are, this is important, the results are expressed as frequency counts, should be counts they are, and the expected frequencies are all at least 5. If so, the counts will be approximately normally distributed, and obviously the expected values are way larger. The smallest value was this 110 something, 110.67. So they are all larger. Having said that, let's do the test. And we start with H0. The proportion of agree-disagree responses are the same for all subjects interviewed by men and the subjects interviewed by women. And then, in other words, P1, P2, P3, all the way P2, P7, however many. In this case, there were only 4 groups. And or survey responses by men are independent of pollster gender. That is a shorthand explanation of that, and that's the claim. The proportion are different, so that's come to that, or at least one proportion is different from the other, or survey responses by men depend on pollster gender, and it's a right-tail test. Again, there are different ways of writing it. I just want to make sure that you're exposed to those. Let's calculate the test statistic, in which case chi-squared summation of O minus E quantity squared, and this degrees of freedom. So for this one, 560 minus 578.67 quantity squared divided by 578.67 plus, for this one, 308 minus 289.33 quantity squared over divide by 289.33 quantity squared, and the rest of them. So, and this is the last one, 92 minus 110.67 quantity squared over 110.67. Here's the test statistic. Degrees of freedom. How many rows? 2. 2 minus 1 is 1. How many columns? 2. Please don't count the total, okay? 2 minus 1, 2 minus 1, we get 1. Alpha is 0.05, and therefore, here's the chi-square table. We look for 1, and it's a right-tail test. So 1 here, 0.05 here, and when we put them together, the answer is 3.841. And if we do the drawing, 3.841 test statistic is way larger than that, puts us way into the rejection region. Therefore, reject H0 or reject independence. So if you're rejecting a claim in essence, the claim becomes false. There's not sufficient evidence to support the claim that the proportion of agree-disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. There is sufficient evidence to reject the claim of equal proportions. Survey responses by men depend on pollster gender. Please understand, these are various ways of answering it. You don't have to answer all those, but I'm just writing. This is one way. The red one is another one, and the green one is the third one to answer that. But you don't want to, write. I mean, I just want you to be familiar with all of it. If we go with two-tail test, we get those two values, and definitely larger than that. So the two-tail test comes from this two, okay? This area, okay? And take it from there. 0.975, 0.025, and that's how we come up with the two-tail test. All right. Test of homogeneity using the following table. With a 0.05 significance level, test the association between people living in a city and becoming infected with a highly resistant bacteria. So, bacterial condition, okay, either infected or not infected in the city. Here's the living location. In the city, this many, 4,239 get infected, and 12,900 don't. Outside the city, 5,923 get infected, 18,986 don't. So that's the table, and we're going to take it from there. Having said that, the H0, whether a person is infected, is independent of whether a person lives in the city or outside the city. P1 equals P2, P3, all the way to P7. There are four of them in this case because there are four pieces. Whether a person is infected is dependent of whether the person lives in the city or outside the city, and it makes it a right tail test. Test statistics, summation of x squared. X squared is summation of O minus E quantity squared over E. So we have to calculate the expected frequency. And expected frequency, to do so, we are going to sum up here. We're going to add this column, this row, and this row. Over here, we put it here. Over here, we put it here. So we get the total of these two, the rows, and here's the grand total. Okay. So, for example, for this one, again, just to remind you, the calculation would be the product of these two. Here's the row sum, here's the column sum. 10,162 times 70,139 divided by the grand sum of 42,048. And you get 4,142.088. And of course, you have to do that for each cell. There are 1, 2, 3, 4 cells. Okay, that's one P1, P2, P3 really stops at P4. 4 cells, okay. I'll put P7 in case we have more. Okay. Now the expected frequency, we calculated for one cell, and here's the rest of them. And you can use any technology. For example, Excel is used, and with more decimals. Now, you can run again, continue with the Excel. O minus E quantity squared over E, infected outside, and so forth. So that means, for example, this one minus this one, quantity squared divided by 4142.08 gives you this one. Okay, just as an example. So the idea is 4239 minus 4142.088 quantity squared over 4142.08 all the way to the last one. That is how it's calculated. These are the values that we must add up. So add all those values, and that is your test statistic. Critical value, it's just like before. Alpha is 0.05. There are 2 rows and 2 columns. 2 minus 1, 2 minus 1 results in 1. And so chi-squared is 3.84. Clearly, if you were to graph this, this is the critical value, and test statistics puts us way into the rejection region. So reject H0. As far as technology is concerned, by the way, degrees of freedom, alpha, chi-squared test, so on and so forth. It has all those values, the p-values, and so forth. So this is technology. More specifically, this is using Excel. And having said that, these are the values. And again, notice this was calculated here, okay? And the critical value, 3.841, of course, with more decimals. And here's the p-value, alpha, which is less than alpha 0.05, same result. So having said that, the decision is reject H0, that means reject independence. The claim becomes false because that's part of H0. And there is not sufficient evidence to support the claim that whether a person is infected is independent of whether the person lives in the city or outside the city. And you're done. The second method to mention that is whether a person is infected is dependent of whether the person lives in the city or outside the city. As far as technology, here's the p-value. And let's say we stop at 4, next to it is 6, goes up to 5, 0.025, clearly is less than alpha of 0.05, and we get to the same decision, reject H0.